This conference will now be recorded.
And we're going to focus on two basic classes that Yaskawa conducts today. We're going to say a few things before we start them. And they will be basic motor theory and basic drive theory. These are two building blocks that need to be at the ground level before we can move into more advanced understanding of the subject matter that we cover in these classes. And before we can even do that, I thought it would be important to discuss for a minute the concept of magnetism and electromagnetism. These are physical properties that differ slightly from each other, but are also very much interrelated. Magnetism is a physical property of a material, doesn't require an external electric force to create it. It is innate in the magnetic material. And a good illustration of that would be a simple magnet, which I will show you now by sharing the screen. So this is the picture of the electromagnet, and of the magnet, not an electromagnet. And what you can see here is a rectangular magnet. At the top, let's call that arbitrarily the north, and the bottom is the south pole of the magnet. And what you see around the rectangle are iron filings that, due to the magnetism of the magnet, have aligned themselves to show you roughly the shape of the magnetic field. Now you can see that they align roughly along the axes from north to south. When we talk about magnetic field strength, we talk about a concept that actually doesn't exist, but it allows us in our human minds to understand magnetism better, and it's called lines of flux. And so you see that these iron filings line up and create certain lines, if you will. The denser the lines of flux are, the stronger the magnetic field. So when we talk about a very strong field, we think in our mind about more density in the concentration of lines of flux. So, I'm always challenged at moving things around on this screen. So now I want to show you some other concepts of lines of flux, because bear in mind that, again, this is a pictorial concept. There are really no, if you go and if you could feel a magnet, it doesn't have these lines. It's just a way of representing magnetic concept to the student. And it started because when we put iron filings around a magnet, it kind of looks like it's created lines. So the conceptual graphic on this is here. North, south, and then we represent the lines of flux with lines that go from the North Pole to the South Pole. This concept of magnetic strength is extremely important, and conceptualizing it and making it easy to understand is therefore important, because electric motor torque is completely dependent upon the density of the magnetic fields that we create. Now, one other thing I'd like to talk about before I start the excellent video from Yaskawa is that if you take a copper or any conductive metal bar, just a rod, say quarter of an inch thick and a foot long, and you pass it through the quote-unquote lines of flux of a magnetic field, you will create current flowing on that conductor. And that is electromagnetism, which is to be differentiated in your mind from magnetism. Electromagnetism flows as long as we are pushing the rod through the lines of flux of the magnet. The minute we cease that relative motion and the rod stays still relative to the lines of flux of the magnetic field, the electromagnet ceases to exist. The lines of flux on a magnet material do not cease to exist. They exist without an external electric current. Thus, one of the differences between the physical property of magnetism versus electromagnetism. And the other thing that we want to understand is that we can enhance the lines of flux on an electromagnet, say a bar of aluminum, which is not magnetic in and of itself, so it has no inherent magnetism, but it can become an electromagnet if I pass it through the lines of flux of a magnet. And if I put a piece of iron next to that aluminum, the magnetic properties of the iron will enhance the density of the magnetic field created through electromagnetism in the aluminum. Similarly, for a copper rod instead of the aluminum rod, which is why you find that motors are copper windings, transformers are copper windings. Westinghouse at one point in time used aluminum for the windings of their transformers, but they always are wrapped around iron called back iron, because that enhances the flux density. It increases the flux density. So as we get into the video about motors from Yaskawa, you will see that the copper windings, which could be any conductive metal, we happen to use copper for a combination of its effectiveness in becoming an electromagnet and the cost associated with using copper and some of the ductile properties of copper. But aluminum has been used in the past. Aluminum, by the way, is a less effective conductor than copper. We could make a really effective motor by using gold, which is a more effective conductor of electricity than copper. Effective in this particular case being defined by the amount of resistance. There's less resistance to current flow in gold than there is in copper. For obvious reasons, we don't do that in industry, mainly because of the value of the materials. But we could theoretically do it with any metal that conducts electricity. So with that concept of magnetism versus electromagnetism and the enhancing effect on electromagnetism flux density, lines of flux, using back iron. With those concepts in mind, let's go ahead and start the e-learning session from Yaskawa on electric motors.
Technical Training Department of Yaskawa America Incorporated presents Induction Motor Basics, understanding how an induction motor works. Hi, I'm Steve Kaler. Three-phase induction motors are the most commonly used AC motors around. You'll find them in literally thousands of applications. With the ability to produce a lot of torque, three-phase induction motors typically power large industrial machines used for product manufacturing, processing, and other applications. Their simple construction, relative low cost, and low maintenance are the main reasons for their popularity. In this program, we're going to look at how an induction motor works and provide you with some basic information on the induction process. We're going to start by listing the components that make up a three-phase induction motor. Then, to help you understand how...
Whoops. I apologize for that. I must have done something, I touched something I shouldn't have touched. Let me regroup here. How did I just turn everything off? Wow. Bear with me 1 second while I correct that. Very interesting. Okay, let's go back here. There we go. My apologies.
Used for product manufacturing, processing, and other applications. Their simple construction, relative low cost, and low maintenance are the main reasons for their popularity. In this program, we're going to look at how an induction motor works and provide you with some basic information on the induction process. We're going to start by listing the components that make up a three-phase induction motor. Then, to help you understand how they all work together and the role that each component plays, we'll review the theories of induction and electromagnetism. Next, we'll explain the difference between synchronous speed and rated speed, how the number of poles affect the stator and rotor, and discuss speed-torque curves. We'll define and compare NEMA motor designs, then take a look at the information that is typically found on an induction motor nameplate and explain what each specification means. And finally, we'll take a look at the various types of motor enclosures. Now, at the end of each section, we are going to ask you some questions to review the points that we have covered. Oh, one note before we start. In many applications, the speed of a three-phase induction motor is often controlled by a variable frequency drive. The information we present today will give you a good understanding of three-phase induction motors and prepare you for the next video in our series titled Variable Frequency Drive Basics. Let's get started. Let's start by identifying the components of a typical three-phase squirrel cage type induction motor. Inside the stator frame of the motor are the stator and the stator windings. The stator is made up of a series of stacked, insulated, and compressed iron slices with cutouts or slots through which we run the stator windings. We use stacked metal slices to reduce electrical losses in the system. Centrally located within the stator is the rotor. rotor is basically a cylinder with an iron core, which is also made up of laminated slices, just like the stator. The rotor has conducting end caps on each end and conducting bars running through the slots in the laminated slices that connect to the end caps.
So like I said before, those conductors that he just highlighted, which in this case happen to be aluminum, and the back iron, which are the laminated steel iron alloy discs.
The result is a rotating cage that looks similar to a squirrel cage. That's why induction motors are commonly referred to as a squirrel cage motor. The rotor is attached to the motor shaft. Bearings support the motor shaft, allowing the shaft and rotor to rotate as it remains centrally positioned within the stator enclosure. The shaft transports the mechanical energy created from the rotor to the load, and an air gap between the stator and rotor eliminates any physical contact between the two components. Protecting the components is the enclosure, which consists of the motor frame and the end bells. The end bells contain bearings which allow the rotor shaft to turn freely on its axis. Now, the type of enclosure can vary depending on the motor's application. We'll talk more about the different types of enclosures later. All right, before moving on, here's the first question. What are the two major components of an induction motor? The answer is the stator and the rotor. These components work together to convert electrical energy into mechanical energy. In this next section, we'll talk about how these two components interact with each other to create electromagnetic induction. We'll start with a definition. So, what is electromagnetic induction? Electromagnetic induction is a process in which current is created in a conductor by moving it through a magnetic field, or by having the magnetic field move or change around a stationary conductor. In a three-phase induction motor, the stator produces the varying, or to be more exact, rotating magnetic field needed to initiate and maintain the induction process. And let's look at how that's accomplished. As we described earlier, the stator has a core of individual laminated plates that are laminated together. These plates have slots in them, which allow insulated electrical windings to pass through the core. The stator windings are distributed around the stator in such a way that when current flows through them, the stator produces a magnetic field. To better understand how the magnetic field is produced, think about the electromagnetic demonstration you may have seen back in science class. An insulated copper wire is wrapped around a nail. When voltage is applied across the wire, current flows through it, and the nail becomes an electromagnet. In this case, you can think of the nail as the stator's core and the copper wire as the windings. Certain metals, such as iron, like this nail, have magnetic properties where the atoms are randomly oriented. This random scattering of atoms cancels any natural magnetic field. But when current is passed through the coil of wire, it produces a magnetic field which forces the atoms to align in the nail. These aligned atoms combine to produce a strong magnetic field from the nail. And the same is true of the stator's core. Three-phase induction motors use balanced three-phase power. The phases are electrically separated from each other by 120 degrees. When you apply alternating current, or AC, the flow of electrons reverses direction halfway through the cycle. To understand how quickly this happens, remember that the standard AC power frequency in North America is 60 Hertz. And that means that current flowing through the stator repeats one electrical cycle every 16.6 milliseconds. And that's faster than the blink of an eye. Here's an example of a simplified model. You can see that the stator is mechanically stationary, but when we combine three-phase alternating current with the correct placement of the stator slots, we create a rotating magnetic field. Now let's look at the rotor and see what role it plays in the induction process. The rotor, with its iron core, conducting bars, and conducting end caps, is constructed to conduct electromagnetic current. As the stator's magnetic field rotates, it induces voltage in the bars of the rotor. As the rotor bars are shorted at both ends using end rings, there is now a closed path for the flow of current in the rotor bars. This, in turn, aligns the atoms in the iron cores of the rotor to produce its own magnetic field, which opposes the magnetic field produced by the stator. This happens because any induced electromotive force always produces current that opposes the force of the source magnetic field. So, the rotor's magnetic field opposes the stator field, which causes it to repel from like poles and attract to opposite poles. This causes a constant chase as the rotor is attracted and repelled by the rotating magnetic field of the stator. We've covered the stator and the rotor, and we have seen how each has their individual function in the induction process. But for induction to take place, there's a third element needed, and that's relative motion. Generally speaking, relative motion is a calculation between the speed of one moving object relative to the speed of another moving object. In this case, the relative motion between the rotating magnetic field of the stator and the rotating rotor. As you can see, the rotor rotates slower than the stator. How much slower depends on the motor's external load and how much energy is lost internally from friction, induction leakage, and other causes. Now, here's another question. Is the rotor connected to the three-phase incoming power? The answer is no. The stator creates a rotating magnetic field, which induces a voltage in the rotor bars, which are shorted on the ends. That allows current to flow in the rotor, which then creates its own opposing magnetic field to the stator field. The difference between the speed of the magnetic field and the speed of the rotor is called slip. To help you understand slip, let's take a moment to define some terms that you'll need to know as we move forward. The speed of the rotating magnetic field in the stator is called synchronous speed. You can calculate synchronous or sync speed by using the formula 120 times F over P, where F is the frequency of the AC power supplied and P is the number of motor poles. We'll talk about motor poles in a second. So, with some simple math, you can see that a 4-pole motor connected to a 60 Hz power source would have a sync speed of 1800 RPM. The mechanical speed of the rotor is called the rated speed. A rated speed is based off a motor's rated load. You can usually find the value for the rated speed on the motor's nameplate, indicating the general speed of the rotor at a rated load. Using our previous example of a 4-pole motor running on a 60 Hz supply, the rated speed would normally be between 1725 and 1750 RPM. So, as you can see, with AC induction motors, the rotor always rotates slower than the magnetic field of the stator. The difference between the sync speed of the stator's rotating magnetic field and the mechanical speed of the rotor is called slip. The amount of slip depends on the amount of the motor's load. The greater the load on the motor, the slower the rotor turns in relationship to the stator's rotating magnetic field. The more this difference increases, the more slip increases. To illustrate slip, pay attention to what happens to the speed of the motor as the load is increased and decreased. You can see that as the motor load increases, the mechanical speed of the motor decreases. And as the load is decreased, the speed increases. This increase and decrease in motor speed to load is called slip. Well, let's take a moment to review. Now, here's another question. Is the rotor's speed the same as the stator's rotating magnetic field speed? No. The rotor's speed is always slower than the rotating magnetic field of the stator in a positive torque application. If both were traveling at the same speed, there would be no induction and the rotor would not be able to create a magnetic field. Induction motors can be constructed to handle various loads and various speeds. One way is to change the number of poles in the stator. You can increase or decrease torque by adding or subtracting the number of poles in the stator. The more poles there are, the slower the magnetic field rotates. Using the sync speed formula, we can explain why that is true. Revolutions per minute equals F, which is the motor's supply frequency in hertz, times 120 divided by the number of poles. So, say you have a 2-pole motor powered at 60 hertz. 60 times 120 equals 7,200. 7,200 divided by the number of poles, in this case 2, shows us that the stator's magnetic field will rotate at 3,600 revolutions per minute. But what happens to the motor's synchronous speed if we add more poles? If, like the example just given, the motor is powered at 60 hertz and we have 6 poles instead of 2, the synchronous speed produced by the stator decreases to 1,200 RPM. You can see by this table that sync speed decreases as you increase the number of poles. So, high torque induction motors have slower sync speeds and lower torque motors of the same size have less torque and higher synchronous speeds. One thing to note, as pole count increases, so does the cost of manufacturing. So most induction motors are 2 or 4 pole configurations. If more torque is needed, most people will opt for a physically larger motor instead of using a 6 or 8 pole machine. Well, it's time for yet another quiz question. If we have a motor with a rated speed of 1,774 RPM, how many poles does it have? And the answer is 4 poles. We know that our rated speed is going to be a little bit less than our sync speed. Looking at this table from earlier, we see that a 4-pole motor has a sync speed of 1,800 RPM. This tells us that if we include slip, we are around 1,774 RPM. In this next section, we'll discuss speed-torque curves and what they mean. Induction motors are used to produce work or to complete a physical task. As they work, induction motors use electrical energy to produce the torque needed to accomplish that task. A speed-torque curve shows you how the torque produced by an induction motor varies throughout the different phases of its operation. Starting torque is the amount of torque an induction motor produces as it ramps up from a standstill. Looking at this example of a speed-torque curve, we can expect the starting torque to be about 150% of rated torque. Pull-up torque is the amount of motor torque available as the motor accelerates toward its rated speed. If the motor's pull-up torque is less than the amount required to accelerate the load, the motor will never reach its rated speed. As the motor continues to accelerate toward its rated speed, it encounters its breakdown torque. Breakdown torque is the greatest amount of torque a motor can generate. When the motor has accelerated itself to its rated speeds, the motor should be producing between 80 to 100% of its rated torque. That is, of course, if the machine has been designed properly. Now, let's look at our example again, but this time, let's pay close attention to the motor torque. As the load is increased and the motor's speed decreases, the amount of torque produced by the motor increases. Watch it follow this line. You can see that torque and current are proportional. That means an induction motor draws more current as you increase the load. So, as the load increases, it increases the amount of current that the motor draws, and consequently the amount of motor torque produced. Okay, let's look at another example. Let's say the machine load gets very large, so large that it causes the motor to produce torque near the motor's breakdown torque rating, and then beyond it. You can see as the load increases, the amount of torque increases and follows this curve. Because of this, the speed of the motor begins to decrease and the amount of current flowing to the motor increases. Current flow in the rotor begins to increase as the rotor becomes saturated. The current in the system as a whole is going to increase. When the motor slips beyond its breakdown torque, it begins to produce less torque, which then causes the motor speed to decrease even more and in many cases stall. This situation usually results in damage to the motor if left in this state due to overheating of the stator. Though typically there's an overload relay that will protect the motor from damage. Well, here comes another quiz question. If we look at the speed torque curve, at what point is the torque at its maximum? Did you come up with breakdown torque? I hope you did, as breakdown torque is the greatest amount of torque a motor can generate. Now let's discuss the NEMA design types and why they are important. An organization called the National Electrical Manufacturers Association, or NEMA, establishes technical standards for the manufacturing of electronic products. NEMA has established standards for 4 different designs of electrical induction motors, which are A, B, C, and D, respectively. Each standardized design has unique speed, torque, and slip capabilities depending on the work they perform. NEMA Design A motors are allowed a maximum slip of 5%.
This is the design that we mostly consider or concern ourselves with when we supply inverter duty motors with the drives. The others are older designs that had their purpose in the day, but the Design A motor is now the predominant motor used in inverter duty rated applications. I will, in a subsequent class on a more advanced level, talk about the Design A and why and how it can be used in a way that actually prevents this stalling or breakdown torque phenomenon that was discussed earlier in this video.
They are similar to Design B motors in respect to torque output. However, these motors are not limited on their starting current. This allows for lower winding impedance, which in turn lowers stator resistance, making Design A one of the most efficient motors from an energy standpoint. Design A motors often offer greater breakdown torque than Design B. Centrifugal fans and pumps are typical Design A applications. NEMA Design B motors are the most commonly used induction motors in the industry. They have a maximum of 5% slip and speed torque characteristics that are similar to Design A motors, but with a NEMA mandated limit to their starting current. Because they can provide good pull-up torque, Design B motors are used in a wide variety of applications. Design B motors can also take impact or burst loads at full speed without stalling. Applications using NEMA Design A and B motors are best suited for drives, a topic that will be covered more in our next installment with Drive Basics. A NEMA Design C motor also has a maximum of 5% slip. Design C motors are built to power equipment requiring high breakaway torque, like positive displacement pumps and conveyors. Similar to Design C motors, a NEMA Design D motor is a squirrel cage motor designed with a maximum slip of 5 to 13%. Low starting current to withstand full voltage starting and very high locked rotor torque. Like Design C motors, you'll find Design D motors powering equipment with high starting torque requirements like cranes or hoists. Design D motors are also well suited to high impact load applications like stamping presses. All right, before moving on, here is another review question. Which NEMA Design motor will be the best for a fan or pump application? The answer? Design A and Design B are both suitable for this application due to their low amount of slip and high breakdown torque.
Again, I want to emphasize that Design A is what we use today, and while B motors are still very common, the Design A has a lot of advantages in terms of being used on a VFD. When he mentioned the Design D motor being used on crane and hoist applications, that comes from a day when we would run those motors from contactors. The Design D motor is a very poor choice of motor when used with a variable frequency drive. Indeed, today when we do crane and hoist applications, we use a Design A motor. It provides much better torque for starting the load and for maintaining the motion of the load, and it has much less slip, therefore the speed is easier to regulate from the VFD. So again, the Design A motor is the primary motor we use for all applications that we consider today with variable frequency drives.
In this next section, we will give you an understanding of the information on an induction motor nameplate. In North America, NEMA also establishes the standards for the information provided on the nameplate. This information is vital to determining the motor's characteristics. Let's look at a typical nameplate. Horsepower is a measure of the motor's mechanical output rating and its ability to deliver the needed torque for the required load and at the rated speed. You can calculate horsepower by multiplying the motor's speed times the amount of torque in foot-pounds and then dividing that sum by 5,252. Torque is a measure of the turning or twisting force supplied by the motor to the load. To calculate torque in foot-pounds, multiply horsepower times 5,252, which is a constant obtained by dividing 33,000 by 2 pi, and then dividing that number by revolutions per minute, or RPM. Motor-rated voltage is the optimal performing voltage of the motor. Because line voltage fluctuates, motors are rated with a 10% tolerance above or below the rated voltage shown on the nameplate. Motor-rated current, which is listed on the nameplate as FLA for full load amps, is the amount of amperage the motor needs when it is operating at full load torque and horsepower. The motor-rated frequency is the frequency at which the motor is designed to operate. In North America, the rated frequency is 60 Hertz. Some motors are designed to work with a variable frequency drive, or VFD. They are rated to run at different frequencies. Motor-rated speed, or full load RPM, is the approximate RPM at which the rotor is rotating when the motor is operating under full load. Motor-rated speed is expressed in revolutions per minute. Motor poles indicates the number of poles inside the stator of a three-phase motor. Motor phase is the number of AC power lines supplying the motor. Of course, with a three-phase motor, there are 3 power lines. The NEMA design letter indicates the motor's NEMA design type, either A, B, C, or D. The letter designation describes the motor's torque and current characteristics. Insulation is crucial in an induction motor. The insulation class describes the thermal tolerance of the motor windings. The letter indicates the motor winding's ability to withstand operating temperatures for specific lengths of time. Motors controlled with a variable frequency drive and/or motors that run at lower speeds usually have a higher insulation class. Service factor represents the percentage of overloading a motor can handle over short periods when operating at rated voltage and frequency. The frame size describes the mounting dimensions, including the foothold mounting pattern and shaft dimensions. Now it's time for a question on nameplates. What is usually given on the motor nameplate, synchronous speed or the rated speed? Rated speed is usually given for a motor. With this, we know how fast the shaft is spinning at the rated load and can easily figure out the synchronous speed if needed. Standards have been established by NEMA for the types of induction motor enclosures. The standards are based on the motor's use and are designated on the nameplate as ENCL. An open drip-proof or ODP enclosure is typically used for indoor applications. The open drip-proof enclosure allows outside air to circulate over the windings while preventing any liquid from entering the enclosure within 15 degrees from vertical. A totally enclosed, non-ventilated, or TENV enclosure uses cooling fins to dissipate heat instead of a fan or vent opening. They're designed for installation indoor or outdoor in dirty and or slightly damp conditions. A totally enclosed fan-cooled or TEFC enclosure is cooled by a motor shaft connected to an exterior fan. Though they're not waterproof, TEFC enclosures are used outdoors in dirty locations. And the final type is a totally enclosed blower-cooled or TEBC enclosure, which is cooled through forced convection by a rear-mounted blower. You'll find TEBC enclosures in both indoor and outdoor applications. Other types of induction motor enclosures include totally enclosed air over, totally enclosed washdown, explosion-proof enclosures, and hazardous location enclosures. And now, here comes our final question. What does TENV stand for? TENV stands for totally enclosed, non-ventilated. Very good. TENV enclosures are designed for damp and dirty environments. As I mentioned at the beginning, this program is just a basic introduction to how AC induction motors work. There's much more to learn, and a good place to do that is at Yaskawa.com. Well, we've come to the end of this training program, but it definitely isn't the end of our commitment to make Yaskawa drives and motion products the best in the industry.
So we're going to move on to the drives class, which is the corollary to what you've just watched, basic VFDs coupled to basic motors. There we go. By the way, this is the website, so these videos can be obtained from the website the same way I'm doing it now. And here we go.
Training Department of Yaskawa America Incorporated presents Variable Frequency Drive Basics. Have you ever thought about what goes on inside a variable frequency drive? After all, when you stop and think about it, these mysterious boxes are really pretty remarkable. They help us save energy, reduce maintenance on our machines, and they give us nearly infinite control over almost any type of process powered by a three-phase AC motor. So how exactly do variable frequency drives, or VFDs, work? And what do you need to know about them? I'm Steve Kaler. Welcome to the second video of our two-part series on motors and drives. In part one, you were introduced to the basics of three-phase AC electrical motors. Today, we are going to look at the basics of VFDs, or variable frequency drives. You may also know them as adjustable speed drives, adjustable frequency drives, AC drives, and inverters. Whatever you call them, what's important is what goes on inside of them and how we use them to control and monitor electric motors. In this presentation, before we look inside of a drive, we'll start with the many applications for variable speed drives, both industrial and commercial. We'll look at other starting methods, ways to start a motor that don't utilize a drive, and next we'll talk about the purpose of variable speed drives, why do we use them. We'll then walk through the typical layout and construction of a drive, and explain the components that make up this device. We'll look at different types of enclosures, and then, to wrap things up, we'll review this presentation with a few questions. Now, before we look at the inner workings of a drive, let's examine the applications that could benefit from a drive. Industrial applications often require very precise control. In the past, these applications relied on complicated gearing and clutches to control the speed of a given system. Examples would include conveyors, cranes and hoists, presses, winders and unwinders, high-speed machining applications, as well as many others. Now, in the commercial market, we are normally trying to achieve a given flow and pressure. This changes depending on the demand at any given time. Fans use inlet guide vanes, bypass dampers, or outlet dampers for flow control. Pumps use discharge valves or bypass valves to regulate pressure. Cooling towers would use a mixture of the two. Using a variable frequency drive for these types of industrial and commercial applications allows us to remove mechanical speed, flow, and pressure control systems that may prove difficult to regulate and could possibly be failure points. Instead, the drive easily adjusts speed and torque to given system demands. Now, on top of that, some variable torque commercial applications can take advantage of affinity laws and use the least amount of energy to meet the given flow or pressure demand. This can lead to energy savings that can have the drive system paying for itself within a short period of time. As we explained in Motor Basics, three-phase induction motors, when applied across the line, run in a narrow speed range, depending on load and motor characteristics. On their own, they're either on or off. However, motor drive systems are often incorporated to allow the system to operate at a wide range of speeds while still producing full load torque if needed. The simplest form of control is a manual motor starter, which is nothing more than a means to manually open and close the contacts to start and stop the motor. Manual motor starters usually include some type of motor overload protection. A magnetic motor starter is similar to a manual starter, except you can remotely toggle a magnetic coil to bring in the contacts as needed. A drawback to both manual and magnetic motor starters is that they do not reduce the inrush current that the system will experience at startup. Primary resistor starting uses resistors to reduce the voltage going to the motor. After a given time, the resistors are bypassed and full voltage is then applied to the motor. These resistors will get hot and have a limited duty cycle. In other words, a limited number of start-stops in a given period applies. With auto transformer starting, we are tapping the transformer at different points, resulting in a change in voltage. After the motor is started, the transformer is bypassed. With Y-delta starting, we connect the motor at start in a Y configuration, which exposes each coil to a lower voltage, then switches over to delta while the motor is in the running state. SCR, or thyristor control. The solid-state device is controlled to pass only a portion of the voltage waveform to the motor. These offer a smooth start to the given system and limit the current draw by the motor. When the motor is up to full speed, the unit then bypasses the soft start function and full voltage is applied. These units have limited start allowances for a given time period, but offer smooth starts instead of the stepped previous methods. So that brings us to the purpose of variable frequency drives. Here are some of the major capabilities a drive provides. If you viewed the Motor Basics presentation, you saw this diagram showing an induction motor's relationship between speed and torque. By adding a drive to the system, we have the ability to alter the speed-torque curve. This lets us take advantage of the motor's characteristics at multiple speeds, instead of being limited to only 60 Hertz. VFDs allow us to match the speed of the motor-driven equipment to the load requirement. Operating a motor with a VFD provides full torque capability over a wide range of frequencies. Having full torque available allows us to use a standard or general-purpose motor in many more applications and situations than we would otherwise be able to. Furthermore, we can limit the output torque of a motor for a given application or point in the process should it be required. Since we now can control the motor, we can program our own acceleration and deceleration, or accel and decel times. Now this will vary depending on the application. For example, a fan can utilize longer accel and decel times, so the motor draws a low amount of current, reducing energy consumption and associated belt wear. On the other hand, some industrial applications require fast response, which calls for very short accel and decel times. Built-in motor protection eliminates the need for external motor protection. In variable torque applications, savings can be seen due to the affinity laws. A small reduction in speed can lead to a dramatic decrease in power usage. We can generate torque at zero speed to hold or lock the rotor, a feature previously limited to servos and mechanical brakes. On the other side of the table, we can now overspeed and run at speeds above 60 Hz, provided the motor is able to accommodate that speed. Remote monitor control means that you can monitor and control the system from your desk or from anywhere in the world where you have an internet connection. We are now going to explain how this device actually works. Now, as we go through, each component will explain what it's doing and how. Together, the components make a three-phase electric motor turn and produce usable work. The three major drive components are control, power, and the main circuit. We'll start with control. For most drives, the operator uses a digital keypad to program the unit for the given application, and in some cases, to operate the drive locally via the keypad. Things like overloads, accel and decel rates, minimum and maximum speed, and many other parameters can all be set through the keypad. For a user looking for some more advanced setups, there are option cards that can be added, which include communication options, feedback encoders, and extended inputs and outputs. For controlling purposes, the user can wire into the digital inputs and outputs and analog inputs and outputs. The I/O terminals also support some communication protocols. Finally, we get to the control board. Now think of this like the brain for the drive. It takes information from the user and drive components and relays the given information or tasks to appropriate areas as required. Let's look at the selectable control methods the drive comes with. These different methods are programmed via the operator into the control board.
We're going to run a little bit over time. I apologize for that. I always try to keep us as close to 8 o'clock as possible. Hopefully you can stick with me, and I will be sending these videos out to you.
Depending on your applications and needs, you will want to choose the control method that best fits your requirements. As we move through each of these methods, control becomes better and better. VF, or voltage by frequency control, is the simplest method. This follows a set pattern, increasing voltage as frequency increases. It's great for fans and pumps. It's also very good for applications that do not need tight speed regulation of the motor. When adding a pulse generator or PG feedback device, the speed regulation becomes tighter and the drive actually knows the speed and direction of the motor. A PG is commonly referred to as an encoder. Open loop vector control is a step up from VF and is great for dynamic motor control and can produce higher torque levels at lower frequencies. This method can also limit torque output. It's great for conveyors and most other general industrial applications. Closed-loop vector control uses an encoder or PG to give instantaneous feedback to the drive. This allows the drive to be used in true torque control mode. This is great for winders, rewinders, and web applications. Zero-speed motor control is also possible. Control methods available for PM or permanent magnet motors may also be available. This motor is similar to the induction motor we talked about before, except the rotor now incorporates magnets to create the rotor's magnetic field instead of the typical shorted rotor bars. Moving from the control side deeper into the drive, we find ourselves at the main power board. This separates the high and low voltage areas, converting signal levels to something the control board can read and output to. This is used for monitoring critical areas of the drive as well as controlling them. The main circuit is where all the heavy lifting takes place, the heavy transformation of power. Most drives now use this same main circuit with a three-phase AC incoming source that is converted into DC, then back to simulated AC going to the motor. Let's start by moving our way from left to right, building our drive, and understanding the components along the way. Starting at the input of the drive, the first device that the incoming line will see is the MOVs, or metal oxide varistors. These varistors are in place to take on any incoming voltage transients or spikes, such as switching transients associated with relay and contactor energization and de-energization. When these varistors come into contact with a high spike, they allow the spike to bleed off to another line and travel safely back out to the incoming line, thus suppressing the spike and protecting the more expensive components in the drive. Well, this brings us to the input diodes, or input converter, or commonly known as the rectifier. Most drives today perform a full wave transformation, which means these diodes chop the AC line and create a DC supply. That is the first of the three major components in the drive. The voltage output from the rectifier is then refined by a filter circuit consisting of large capacitors and, in some cases, a DC link choke. In any system using a combination of a rectifier and a filter, capacitors may result in discontinuous current draw. Now, this results in harmonics being reflected back on the incoming line. Yaskawa has a video titled Harmonics that further explains this topic and ways to mitigate harmonics. The components between the rectifier and the filter capacitors comprise a soft charge circuit. When you apply power to the drive, the unit must safely power up. This happens relatively fast, but we must slowly charge the capacitors in the drive. An uncharged capacitor will act like a short if full voltage is applied to it instantly. This is not desirable because the inrush current may be too high for the rectifier and upstream supply components. Therefore, we use a soft charge circuit to slowly charge the capacitors. The soft charge circuit is made up of a contactor and a resistor. Now, the resistor limits the current flowing to the capacitor. After the capacitor charges, the contactor closes and bypasses the resistor. Remember, electricity, like most of us, will follow the path of least resistance. Once the DC bus capacitors are charged, they act like a storage tank for the drive. The capacitor stores voltage for the system. These capacitors also have a smoothing effect for rectified power. This smoothing reduces the peaks and valleys of the three-phase incoming power that has been rectified. This reduction in ripple helps reduce the wear on the system as a whole. It's also important to note that the voltage level in the drive has now changed by rectifying AC power. The new DC bus voltage can be calculated using this formula. VDC equals the square root of 2 times the voltage of the incoming AC. We now move to the last major section of the drive, the output, or more specifically, the inverter section. The inverter section of the drive is comprised of IGBTs, which stands for insulated gate bipolar transistors. These work together to produce a simulated three-phase AC waveform to the motor. One IGBT will take power to build the upper part of the wave. Then another IGBT building the lower half of the wave. Now remember, we have a three-phase motor, so typically 3 IGBTs are on at a given time to generate simulated AC voltage waveforms to the motor. These IGBTs have built-in diodes that allow current to flow in the opposite direction of the current flowing through the IGBTs as may be encountered when turning the IGBTs off or when exposed to regenerative conditions. However, the rectifier blocks the regenerative energy from flowing back onto the line. This is also one reason why you might encounter an overvoltage trip. Yaskawa does offer systems that have the ability to put power back onto the line. These units use different drive topologies that allow for regeneration. After the IGBTs come the DCCTs, or direct current transformers. The DCCTs monitor output current on all three phases going to the motor. This can be used for control and motor protection. Let's explain how these IGBTs work together to build this three-phase power. The IGBTs are controlled using PWM, or a pulse width modulation scheme. The IGBTs are basically switches that work at a very fast rate. Since they are either on or off, the only thing we can change is the amount of time they are on or off. So, to build this waveform at the beginning, we stay on for a very short period of time. Then we increase our on time relative to the base sine wave we are building from. After reaching the peak, we then start to reduce the on time until the 0 point when another IGBT starts to turn on to create the inverted wave. You will notice that the voltage waveform is almost square, but is happening in the positive and negative regions. And that's because the IGBTs are pulling from the constant DC bus. Voltage reacts very quickly compared to current, which causes this block-type output. The pulses are high in amplitude, but the RMS or root mean square voltage appears equivalent to the motor rated voltage. You will find motors that can handle this PWM style waveform tend to be labeled inverter duty on the nameplate. Now the rate at which IGBT switching occurs is known as the carrier frequency. This switching frequency can be adjusted if need be. Increasing the carrier will result in a cleaner, more sinusoidal current waveform, which in turn will make the motor generate less audible noise. However, this will also make the IGBTs work harder and create more heat within the drive. It may be necessary to derate the output current of the drive to accommodate for the increased carrier frequency. It's interesting to note that the reason a motor is louder when connected to a drive versus across the line is due to this switching frequency. The stator laminations in the motor vibrate, causing this audible noise. Increasing the carrier only brings that vibrating frequency to a level that becomes difficult for us to hear. And this leads to a less audible noise and a quieter motor. Decreasing the carrier will lead to the opposite characteristics. That is, there's more audible noise, but the IGBTs don't have to work as hard. As a result, we have a cooler running drive. You can see how the fundamental output frequency referenced in blue reflects onto the actual output via this given carrier frequency. When we are finally brought to the output current wave for a given phase, as you can see, this looks sinusoidal. Well, remember that an induction motor is basically an elaborate inductor. And what do inductors mainly care about? That's right, current. Well, the drive is sending the motor a relatively nice and clean sine wave so it can do its job, which is to turn a shaft and produce work. Well, now that we've walked through the inner workings of a variable frequency drive, let's head to the lab and take a look at the outside of the box. You'll find information about each drive on its nameplate. The front cover has information such as a model number and serial number, which you would need if you ever have to contact tech support. You'll also see the voltage class and the amp rating in normal and heavy-duty situations. On the side of the drive, you will see the full nameplate with all ratings and certifications. Depending on the type of environment the system will be exposed to, the drive enclosures will vary. NEMA 1 enclosures are designed for indoor applications and provide protection against finger contact with live electrical components and a limited amount of falling debris. NEMA 12 steps up the protection. It's also designed for indoor applications, and all openings have filters that require regular maintenance. The filters protect against circulating dust, falling dirt, and non-corrosive drinking water. NEMA 4X enclosures are designed both for indoor and outdoor applications and provide a degree of protection against falling rain, hose-directed water, and damage from ice formation. NEMA 4X also provides protection against corrosion. Let's head outside and take a look at a NEMA 3R. NEMA 3R enclosures are designed for outdoor applications. They provide protection against falling rain, sleet, snowballs, and prevent corrosion from the formation of ice on the enclosure. Rain hoods over the ventilation holes prevent rain and insects from entering the cabinet. Yaskawa 3R enclosures also include filters to provide some protection against the ingress of dust and dirt, which is not a requirement for UL or NEMA specifications. And now it's time for your favorite part of our program, the review questions. Number 1, does a motor draw more current when started across the line or when started using a VFD? When starting a motor across the line, there will be an inrush of current. This is due to an instant frequency of 60 Hz applied to the stator at full line voltage, and the rotor must then play catch-up. That in turn causes excessive current draw. The drive has the ability to slowly increase frequency and voltage going to the motor, thus limiting any inrush. Question number 2. What does the acronym MOV stand for? That's right, metal oxide varistor. These help dissipate some high incoming voltage transients that could damage the internal VFD components. Question number 3. Does a drive output a purely sinusoidal AC voltage waveform? No. The drive outputs a simulated AC wave that uses PWM, or pulse width modulation, to build the waveform.
Now, of course, that is yes if you use the U1000 matrix drive, which we've gone over in this class in the past, and we will review again in a future class.
And now for our final question. Can a drive be mounted outdoors? Well, of course it can be, if it's enclosed in a NEMA 3R cabinet. A 3R cabinet is made to withstand rain and sleet.
So, thank you for allowing me to go a little bit over time today. Those are two really important foundation topics for our understanding of the subject matter of variable frequency drives, and I hope that you got a lot out of it. But it's 8:10, well over time. Thanks again for allowing me to go over. It's time to go to work. See you next week.